Simon Grabowsky. Simon is probably one of the very best known people in our field. He also belongs to the most active people in quantum crystallography. Now Simon is a researcher in physical and structural chemistry, serving as a research group leader and private docent at the Department of Chemistry, Biochemistry and Pharmaceutical Sciences at the University of Bern, and this is since August 2019. Prior to this, he held the position of extraordinary professor at the University of Bremen from October 2015 to July 2019, where he also held an Emineder fellowship of the German Research Foundation. His independent academic journey started as an Australian postdoctoral fellow at the University of Western Australia from January 2011 to January 2014, followed by an assistant research professor position at the same institution. And as we know, Simon was collaborating there with Dylan Jayatilaka. Dr. Grabowski completed his doctoral studies at the Freie University at Berlin, obtaining a PhD in chemistry in February 2010. And his doctoral research was conducted under the guidance of Professor Peter Luger, who is extremely well known in Poland because he published this book about X-ray crystallography, which actually is a kind of a duty for Polish, say, crystallography students. So they all know this book, at least at our department. Simon worked in the field of experimental electron density determination via high-resolution single crystal X-ray diffraction. In recognition of his extensive contribution to the field, he successfully completed his habilitation in physical chemistry at both at the University of Bremen and also at the University of Bern. Are these the only habilitations, Simon, or do you have some more habilitations than this?
No, not at the moment. I could get one in inorganic chemistry. I'm thinking about it actually, but no, for the moment.
Not yet. Okay. His research is focused on X-ray wave function refinement, relativistic effects in electron density, and electron density property relationships in inorganic chemistry. So Simon, the screen is yours.
Yeah, thank you very much, Krzysztof and Paulina, for the invitation and also for organizing this event, which is so successful. I mean, beyond everything we anticipated a couple of years ago when this was started. So I'm happy to talk about the relationship or the mutual benefit between quantum crystallography and chemical bonding analysis. The focus should be on chemical bonding analysis, but nevertheless, I should start with explaining to you or showing you the means and the techniques that we use for getting to the, let's say, interesting chemistry. So quantum crystallography, it does start with the single crystal X-ray diffraction experiment. We need extremely high quality single crystals, and we need to measure very high quality diffraction data, especially, I want to point out, especially low order data should be of high quality. The information about chemical bonding and also the information about hydrogen atoms are in the low order data. Of course, having high order data of high quality is also preferable, but I think the quality of the low order data is what makes a chemical bonding study in the end reliable. So then after we collected those data either at home or at synchrotron sources, modeling or deriving the chemical model in the computer, that's where we use different techniques from, let's say, standard Shell XL type independent atom models. And then analyzing the structure is analyzing the electron density distribution, not only the atom positions. So talking about the model, or what we do in the computer, for now more than 100 years, the standard model is that of spherical, non-interacting atomic electron densities, which are fully transformed to the scattering factors or form factors that are used in the refinements. So this is the spherical model of electron density. But if we want to discuss chemical bonding, then obviously, as you see from the examples, we need to go to different models. We need to go to models that include the non-spherical or the deformation electron density. And that can be done in various ways. The let's say most established one is the multipole model, pseudo-atoms with multipolar functions, but I will not talk about this today. I will not talk about maximum entropy methods either. I will talk about these techniques where we use wave functions and molecular orbital coefficients directly to adjust them, fit them to the experimental data, and analyze them chemically. That part of quantum crystallography where we use wave functions has been summarized by Alessandro, Hans Beert, and myself a couple of years ago, and I refer to this paper because I don't want to go into the theory too much in this talk, but rather come to some interesting examples. Now, as an overview, or as an let's say the philosophy behind it, is that we have two aspects of quantum crystallography, or of the problem. The first is, and the first in terms of this is the first step that has to be executed, is where we use quantum mechanics. So we use quantum mechanically calculated wave functions to support crystallography in a way that we get non-spherical atomic form factors for an improved geometry and improved atomic displacement parameters upon least squares refinement. But the converse of that is also possible, and that is usually the second step that we perform, where the experimental structure factors that we measure in our, let's say, high resolution, low temperature X-ray diffraction experiments support the interpretation of the quantum mechanical wave function. So I call this wave function with all information from experiment. I come back to what I mean here in a minute. So the first aspect can again be, I mean, there are different techniques how to do that. What we use here is, let's say, classical Hirschfeld atom refinement that was introduced by Jaya-Tilaka and Dietrich a couple of years ago, and then let's say summarized into a protocol which is now already nearly 10 years ago. There are other ways of doing this. Michal Chodkiewicz, for example, has papers about different partitioning schemes, but this is the one we use here. And then for the second step, the wave function fitting, it's again Dylan Jaya-Tilaka's technique of X-ray constrained wave function fitting. And I also come back to that in more detail in a minute. But for all the examples I show later, we always use a subsequent execution of first Hirschfeld atom refinement, then fixing those parameters, coordinates, and ADPs, and then fit the wave function based on those fixed geometrical parameters. We can do this iteratively. We can go back with the adjusted wave function to the Hirschfeld atom refinement, but that's something we have still not published, although we have managed to do this already 5 years ago. But nevertheless, we call the whole procedure X-ray wave function refinement. This is the subsequent execution of these two steps. First, structural refinement, adjusting parameters, structural parameters, then adjusting molecular orbital coefficients. Okay, just a few spotlights about Hirschfeld atom refinement and wave function fitting. So for the crystallographers in the audience, you are probably familiar with the software OLEX 2. And now the most broadly used software for Hirschfeld atom refinement. There are others. Again, for example, Discount by the Warsaw Group is Nosferatu, non-spherical atomic form factors in OLEX2, developed by Florian Klimis and maintained and programmed. So here, I use this just to go once through the basic steps of Hirschfeld atom refinement. The input selection is done in the GUI, in the OLEX2 GUI. So you can grow the structure, you can use a cluster, hydrogen bonding cluster, for example, or whatever is beneficial for the refinement on the screen. Refine that, but you have to use OLEX2 refine now at this stage, not Shell XL anymore. And then from the, now Nosferatu basically kicks in. From the CIF, the XYZ coordinates of the atoms are written into an input file for quantum mechanical software, ORCA mostly. The wave function from that is then interpreted by Nosferatu in a way that this Hirschfeld atom partitioning is carried out, and we get tabulated scattering factors, so human readable or binary. I think that's a new development, also binary files of the scattering factors that can then be used again in a normal standard least squares refinement in OLEX2, and this is an iterative procedure. So the main benefit here is for hydrogen atom positions. I show you here again in this diborane structure that, let's say in the routine or old way, spherical atomic electron densities are used, but in a chemically meaningful way, we need to include the deformation into the bonding regions. So then an isosurface of the electron density of the boron atom, or more precisely an isosurface of the Hirschfeld atom is shown on the right here, and you see the deformation into the tetrahedral kind of bonding environment. Now this is especially important for the hydrogen atoms, because in the independent atom model we assume there is a core electron density, which in fact there isn't for a hydrogen atom. So the difference between the two shows you clearly how electron density is shifted from this non-existent core into a much more diffuse valence region for the hydrogen atom. And that is what allows us to determine hydrogen atom positions and also their ADPs, so anisotropic displacement parameters, accurately and precisely. And for organic compounds, and now there's also work for, let's say, transition metal hydrides and so more of the periodic system of the elements that are in agreement with results from neutron diffraction. So that is why we use at first Hirschfeld atom refinement, because we have a geometry that we can rely on. And then we perform the X-ray constrained wave function fitting, where I said this again, but I said this before, but again, we adjust or fit the molecular orbital coefficients to the measured structure factors. And with that, we include experimental information into our model wave function. One thing here that I want to highlight, and that's part of this recent review, when you look at the wave function, you have two center functions or two center integrals that you need to solve. But in crystallography, we have one center functions, atom-centered functions. So we need to approximate or use approximations for one center probability functions. And for that, we again use Hirschfeld atoms in X-ray constrained wave function fitting. Okay, now to what extent or to how meaningful is the information we get from the experiment in that model wave function? Let's start as a thought experiment from an isolated molecule and Hartree-Fock wave function as a starting point. So we basically neglect electron collation, we neglect the polarization via the crystal field, and then that is exactly the information we can now introduce from via the fitting procedure. So electron collation, to a certain extent, is included into the wave function. The polarization by the crystal field also, but that's a bit more complex relativistic effects. But noise and error as well. So we always have to be aware that Of course, we also fit the noise and the error. With that, I mean statistical and systematic into the wave function and have to deal with that. And I want to discuss that a little bit more. So we have looked again, this is a paper from earlier this year and work mainly by Manu Hupf and Florian Klimis. We have looked again at how would the experimentally obtained electron correlation and polarization effects compare to reference calculations, and how much does the noise affect this fitting. So what you see here is in the top row, that's the urea molecule. In the bottom row, that's the L-alanine molecule. On the right, in the right column, that is the theoretical reference. So this is coupled cluster calculations minus Hartree-Fock calculations. And you see the difference electron density. So the shift of electron density from, which is red, to which is blue. So in the reference calculations, it's always the shift of electron density from the valence regions, bonds or lone pair regions, here from lone pairs, from bonds back into core regions. That is what electron correlation does. That is not new, but let's now look at how this compares to fitting in the electron correlation effect. And you see that there is a similarity. Yes, it's again this shift from valence to core in both molecules. You see the lone pairs, you see the bonds, but then there are dissimilarities as well. So now you can judge whether this is too risky to include all of the noise, or if it's beneficial to have this additional physical effect in the wave function. And I show you in, let's say, 5 slides or some slides from now that an example where this is really beneficial, especially the electron correlation effect. For polarization, it's a different effect. Qualitatively, again, the theoretical reference here, we see now more dipolar features at the atom positions, but they are reproduced more or less qualitatively in the experiment when we fit to the experimental data. So before I go to detailed bonding analyses, I just want to make the point again that between the Hirschfeld atom refined results and the wave function fitted results, we are fitting at the verge of the significance level. So let's go back to the residual electron density map as it looks after the independent atom model. Then we have these clearly systematic features left in the bonds, which we have not included in our model. This would be the R value after Hirschfeld atom refinement, after including the non-spherical atomic electron densities. We have included that non-sphericity, and you see the drop in the R value. And now the last little bit, the fitting will now take those features which are left, and this is, in total a drop of 0.4%. And that is what we include in the wave function. That is what we analyze chemically. So we always have to be aware we are fitting at the noise significance level, but also there is still information in the data. Okay. Now I want to come to chemical bonding, which is actually the topic of today's double feature. And I like to refer to that kind of bonding analysis that we do as complementary bonding analysis for 2 reasons. The first reason is what I've just discussed in the last 10-15 minutes, the complementarity between the experiment and theory. And here we merge experiment and theory. That's one aspect. But the second aspect is that now how to analyze the bonds. There are so many different ways of looking at this quantum phenomenon of bonds, which is not an observable in quantum mechanics. So I will show you that I believe that we need to look at different bonding descriptors from different theories to come to a conclusive result, and that is, not only topology of electron density, not only natural bond orbitals, but a judicious choice of these different methods. And I show this book here again because also Matthias Bickelhaupt, our second speaker, has contributed with a chapter here. So I think this is a good starting point, or good starting point for a connection. Okay, the first study, again, something that Florian Klimes did. So I realize now that basically all the results here come from his work. It's not true, but the last example not. But here, again, Florian Klimes' work in his PhD. And all the results based on X-ray wave function refinement, except for one, which I will also point out. But anyway, now let's focus on the chemical story here. Here we looked together with our Japanese partners on or at olefins, ethylenes, double bonds, and how they change the character or their resonance forms if we polarize them in a push-pull manner. So push-pull manner means we have electron donating groups on one of the carbon atoms of the olefin and electron withdrawing groups on the other side. And then, because of that, this second resonance form, where we have a lone pair at the carbon and a charge-separated form, becomes, also, I mean, we need to consider it, right? And even more, if we, and this is the molecules we synthesized and looked at here, if we somehow restrain the molecule to be still planar, and we do this here through intramolecular hydrogen bonding, then we assume, that's our hypothesis, that resonance form A will prevail for this form. But if we remove this possibility of this intramolecular stabilization of the geometry, then we have the twisted form. And here we assume that resonance form, B or D, so here in the twisted way, D, the charge-separated form will dominate. So is this true? And this is where the complementary bonding analysis starts. Let's first look just at the bond length. So this is the twisted, this is the planar geometry, and the bond lengths are very similar. They are more in the regime, both of them, of a single bond, and very similar. So actually here, the bond length doesn't tell us much about the bonding character, which is an important thing to note, because that's a usual notion that bond lengths give us, bond strength and give us the full picture, which is not true. We have also enlisted the help here of a conjugated olefin, one double bond here, one here. So that would be the bond length of a conjugated one, still strongly polarized. Now, the second thing is we do look at the electron localizability indicator. It would show us regions in space where electron pairs are localized, and we show isosurface representations always at the same iso value throughout the series. You see that in the case of the twisted form, we do find the lone pair at the carbon atom at C2. And we do find a bonding electron pair, and at least at that iso value, they are not merged, and we find different basins for them after topological analysis. Now, if we go to the planar form, we still find basins for both, so separate basins for both the lone pair and the bond, but you see the form already changes, and then in this polarized but conjugated double bond, you get more what we expect for pi bonding, this banana shape, because it's polarized. So this still is not 100% conclusive, so we cannot say which resonance form dominates. Both certainly play a role in both cases. Now, and this is where the complementarity of the methods really becomes important. Now, we looked at carried out energy to composition analyses in the Morokuma, or I could say Bickelhaupt type of way, in the ADF software. But this is not on the constrained wave function, because of the, in ADF we use Slater type basis sets, and from the wave function fitting we have Gaussian type. So this is not compatible. So this is theoretical calculations on the Hirschfeld atom refined geometries. And we also came up with a scheme where we calculated model compounds and subtracted the single bonding contribution, so the this is the energy for the full molecule minus the energy of the single bonded contribution through model compounds. And now you see that the double bond formation energy, the orbital overlap, just for the double bond, for the second pi bonding, is about twice as high for the planar compared to the twisted. So this is more in line with the original hypothesis. And then natural resonance theory in the framework of NBO will give us percentage or weight or percentage contributions of the different resonance forms A over B. And now we have a, let's say, nearly 100% contribution of form A. Form A is the charge separated form for the twisted geometry. And for the planar geometry, we have 20 to 80 in favor of B, which is the double bonded form. And then we have, let's say, close to 100% for B here in this conjugated form. So this here now gives us a clear picture on which resonance form dominates in which case. And a point I want to highlight here is now this is due to electron correlation. If we neglect electron correlation by calculating the same information with the Hartree-Fock wave function, it's 80 to 20 for the other wave, for the charge separated form. If we then use DFT, we still have this preference for the charge separated form, and only if we include more higher level electron correlation effects, we get what I would consider the correct result, because we confirm this with our experimentally fitted wave function, 80% for form B. So this is where I think the complementarity of both experiment and theory and different bonding descriptors helps us to fully understand the chemical bonding. Now, the next step here, this is a paper from this year, is where we again look at this push-pull system, but now by increasing the length of the conjugated system. Here we have 3 formal double bonds, 2 and 1. And I only look at one of the examples now because it's getting too much information otherwise. Now, the question is the same as before. Would the charge separated resonance form, where we have a lone pair at this carbon atom here, dominate, or the neutral form? And again, from bond length, that's not conclusive, or in other words, it shows us that both forms have a significant weight and both resonance forms contribute to the bonding. And again, this electron-localizability indicator shows us a similar story. All the bonds have more or less the same form, but in addition, we find the lone pair at the carbon atom. Now, only if we go to bond orders, and I show only the NBO way, or one of the NBO ways here, but we have, I think, 6 different kinds of bond orders that give us a similar picture. We see this clear, how do we call it? Sorry, we call it reversing of the bond length alternation order. So what in the neutral form, sorry for jumping, what in the neutral form is a double bond is in fact a single bond. What in the neutral form is a single bond is in fact a double bond. And then these two are more, let's say 1.5-fold bonds. So again, bond distances are not the ultimate truth here, and we look at chemical bonding descriptors. Now for the last 10 minutes, I hope I have 10 minutes left approximately. I want to talk about one of the most highly controversially debated topics in inorganic chemistry, hypervalency for elements of period 3. And of course, I acknowledge that there has been much theoretical work. Again, for example, by Bickelhaupt's team, the ball in a box model goes into that direction. But I want to approach this quite, let's say, naively, or from a fundamental perspective and molecular orbital perspective, and then look at what quantum crystallography can add to the debate. So Actually, in my opinion, there is not much of a story, because this is the textbook I use. It's in German. The textbook I use in first year chemistry, and this is an old edition, 1999. And if you just look at the molecular orbital scheme of the SF6 molecule, in the way that we teach it to the students in the first year, you see that SF6 has 4 sigma bonds. By merging these 4 atomic orbitals with those 6 fluorine p orbitals, that makes 4 bonding and 2 non-bonding orbitals. So we have a total bond order of 4, and then plus 2 fluorine-centered lone pairs, which are part of the molecule, right? This is a delocalized scheme. So very clearly, in the simple molecular orbital scheme that we teach to first-year students, SF6 is not a hypervalent molecule. It's hypercoordinated, but not hypervalent. And I think that's the end of the story. But nevertheless, there is this debate, and it's still not arrived in the chemical mainstream. I don't know if that's the right word. So there's a paper here by Sylvie Gillespie, where they use the electron localization function. It's very similar to the electron localizability indicator we used before in the previous example. And the green domains here are the SF bonds. If you add up all the electrons that are in these 6 bonds, you come up with 6 electrons. So let's say 1 per bond, which is significantly less than those 8 that make up the octet rule. In ELF or ELI, there is a clear preference for electrons being in the lone pairs, and that is the charge-separated bonding model. So now let's look at this from a quantum crystallographic perspective. There is the work by Dietmar Starkes group, and they have pioneered this discussion on hypervalency for period 3 elements from the electron density or experimental, let's call it experimental point of view. This is already now also 20 years ago. They looked at the this hexa-coordinated silicon compound with polarized bonds, and they conclude that the silicon atom in 1 is definitely not hypervalent. That is the result of the topological analysis from the multipole modeled electron density. So what we want to do, or what we started to do, this is not finished, is we try to use simpler model compounds for SF6, which is the PF6 minus anion, and crystallize them with different ammonium salts, because they give very nice crystals. In fact, the crystals are so nice that we have problems with extinction and also anharmonicity that we need to solve. But anyway, this is our model compound for SF6, or I mean, it's PF6, so it's the same question, basically. At the moment, what we could do is, it's not finished, as I said. We look again at the electron localization function and at the count of electrons in the bonds, and we confirm this earlier Gillespie-Sylvie work that there are 6 electrons here in these 6 bonds in total. So clearly, the octet rule has not been broken. And then also we synthesized in collaboration with Gerd Volker Röschenthaler's group those compounds with SF5 ligands, and we are analyzing them as well in the same fashion and confirm more or less the same result. The last and the same result is that there is these significant ionic contributions to the bonding, which give us 4 single bonds, and the rest is lone pairs of the fluorine atoms. Now, the last point here is that there is, of course, also hypervalency that is not only sigma bonding, but also pi bonding. So in those very fundamental compounds, such as the sulfate anion, we would normally draw Lewis structures that would imply that we have hypervalent bonds by double bonds, which we know there's no d orbital participation. So how to explain this bonding from a quantum crystallographic perspective? This is again the work by Starke, where they come to the conclusion that the sulfur-oxygen bond in the sulfate has such a polarized character that the actual SO bond order does not exceed that of a standard covalent single bond. The present bonding analysis therefore rules out the hypervalent description of the sulfate. So again, we just extended this study by looking at the series phosphate, here in a mineral, sulfate, lithium sulfate, and then potassium perchlorate, and looked at the fitted wave function, the X-ray hash atom refinement fitted wave function, to look at more than just the topology of the electron density. So the question is it only these ionic resonance forms with 4 single bonds? These ones here, we rule out. We know since the 80s that d orbitals don't participate in the bonding, so this kind of hypervalency is not relevant. But what about pi bonding now? At first, if we just look at the, here in this case, not the localization, but the concentration of electrons, we do find 3 lone pairs at each oxygen atom, which corroborates such kind of Lewis structure. But that's not the whole truth, because now these lone pairs in the form of negative hyperconjugation or non-classical pi bonding or Randall-Pimentel kind of pi bonding overlap with the anti-bonding orbitals, and this is a significant stabilization. These are the perturbation energies from the NBO scheme. So, and by the way, we managed finally to feed the fitted Fock matrix back into the NBO7 program, which was a huge technical effort. Thanks to Lorraine Malaspina, we managed to do that. So now we can show that we have an increased stabilization by non-classical pi bonding. That, of course, has been known before already by theoretical calculations, but this is from the experimental contributions. And this means that now we can look at the contribution or the percentage contribution of the ionic resonance forms with 4 single bonds, and those forms that would then more express the negative hyperconjugation. But it shows we do have pi bonding interactions, we do have pi bonding electron density, but in the non-classical way. And if we go from the most polarized PO bonds, where those resonance forms dominate with 70%, over the sulfate to the perchlorate, we come to a situation where we have 50-50 between these forms and these forms. And that means if we now count the electrons in these in the vicinity of the chlorine atom, and we use the Durant electron counting scheme, which has been published here, which uses charges on the atoms to then separate space, separate space and count electrons. We see that now we have again more than 8 electrons about the chlorine atom, because the chlorine oxygen bonds are not as polar as the sulfur oxygen or phosphorus oxygen. So since chlorine is quite electronegative and the electronegativity difference here is small, we can argue now again, and I'm happy to argue with you, that now we have a hypervalent description again, but this is not due to, you know, the kind of increased valence or d-orbital participation or back bonding scheme. So here I'm at the end of what I wanted to say. I thank, of course, those people who did the work, and you have seen them, especially Florian Klimis, Man Hupf, also Lorraine Malaspina, and my group at the University of Bern. Thank you very much.
Thank you very much, Simon, for this excellent lecture, which is now open for questions and comments. And so please write your questions on chat. And before the first questions appear, may I ask a question myself? Simon, you are for so long time in the field. What do you see as the, I would say, most serious limitations of quantum crystallography and the biggest challenges of quantum crystallography?
Okay, that's of course not an easy question or a quick question to answer. I think that we are now at a level where we have such a sophistication of the models we use to interpret the data, you know, all these different ways of partitioning the space, all the different ways, including relativistics and all of that, that we are at the limit of what we can actually observe given the data quality. And I think the biggest challenge we will face is to, first of all, improve the data quality and to understand what the actual problems with you know, data reduction, integration, different integration boxes, different integration software are. As long as we don't really understand that, I think we are now at the limit of what we can reasonably interpret in terms of chemical bonding.
Okay, thank you very much. Some people are writing, we can see this, so we'll wait for a moment until they finish writing questions.
Yeah, Simon, in the meantime, can you comment for the wave function fitting? You mentioned at the beginning that you need to have high resolution data, but is it also true for wave function fitting?
No, I think, I don't know, maybe you misunderstood me there. What I wanted to say on the first slide here was, if we don't, on this slide, if we don't use multiple modeling, there's actually no reason to, or no necessity to have high resolution data. If we have very good low resolution data, let's say 0.8 angstrom, that's sufficient definitely for Hirschfeld atom refinement. And also, the wave function fitting is resolution dependent in a way that if we have very good low order data, we have the clearest and physically most meaningful result in the fitted wave function.
So there is a question from Hans Birgi. The negative hyperconjugation is also observed in organic chemistry, ketals and acetals, where it's known as the anomeric effect. Can you comment on that?
I think that's a comment, right? So yes, of course.
Yeah.
Also, let's say hydrogen bonding, intermolecular hydrogen bonding is basically the same effect. It's the lone pair of the acceptor donating into the NH or OH antibonding orbiter. So we could describe this in the very same way.
But are you aware of any experimental results discussing it? I mean, from quantum crystallography. For this, that's my question actually.
Yes.
I don't remember.
I'm aware of much work on hydrogen bonding, of course, yeah. But ketals, for example, would be a good project to study. Sugars, let's say, you know. No, I'm not aware, but maybe. I mean, of course, there is charge density on sucrose, for example, but analysis has never gone into that direction, as far as I know, that you really look at this negative hyperconjugation in such organic molecules.
Another question from Daniel Kamiński. Great results. Which DFT method do you recommend for fast and relatively accurate calculations, possibly similar to those with MP2?
So if it's about such things as looking at resonance forms, then I would not recommend DFT at all, because we see not only with one functional, but also with other functionals, that the results don't agree with the fitted wave function. And in fact, if we use the DFT functional and use that in the fitting, you know, we don't start from a Hartree-Fock wave function, but we start from the DFT wave function straight away. We really change that wave function, that DFT-based or Kohn-Sham-based wave function, into a direction that coupled cluster, for example, would give you. So I'm a bit hesitant to say I would recommend this or that DFT method for such kind of chemical bonding analysis. I think it's a bit risky.
We have a next question from Katumbaro Nidenmati, if I pronounce this correctly, this name. Thank you very much for excellent lecture. Can you please specify any particular aspects of data reduction which you think should be dealt with for improved data quality to improve interpretation?
Yes, I can. For example, absorption correction. You know, when you do in these softwares, there are all maybe 5 different ways that you can click to do absorption correction, face-centered or multi-run, and then Gaussian way, analytical way, Clark-Reed way, and all of them give different details of the electrodensity map in the end, especially if we're looking around the heavy element, which is maybe something that, you know, where electron correlation effects, for example, are very important. But if different absorption correction schemes already give you difference in the electrodensity map, which are bigger than the chemical bonding effect, we don't even need to start to look at heavier elements. And another thing that I think is very important is how we treat the data during the integration. If you just compare Chrysalis Pro, where the integration boxes are refined or optimized during the integration procedure, with something like Apex 4, where you can fix them, you get very different results. There has been nice work by Herbst Irmer and Starke, where they show that this is actually a way to also model thermal diffuse scattering effects, which are again something we neglect. So yeah, these are some of the effects, but I think the biggest problem is that maybe I can only speak for myself, but we don't really understand what the algorithms in such software programs do. So it's very difficult to correlate the findings that we would then sell as chemical effects with those modifications of algorithms and the data reduction.
Next question by Florian Clemens. Thank you for a very nice talk. My question is about the effect of extinction and maybe improper data treatment. How can we ensure that a single outlier, maybe slip through the data treatment, does not damage a specific bond, especially regarding the experience with the PF6 salts?
How can we ensure that is the question. I think we can't ensure it. We have to be very careful. I know with PF6, that is important because it's highly symmetric and we have not as many reflections. But I know one example in one of the boranes that we did back in Peter Luger's group together with Dieter Lenz, where one single outlier in the low order region destroyed the entire electron density map. And we tried to figure out what the problem was. In the end, we refined it unharmonically. I think that was not the correct way. Could have been a Renninger effect or something like that. But it was one single reflection, which was I think, I don't know, 111 or so, very low order reflection. I think we can't ensure that this doesn't happen, but I think we have to look at this every single time in every single measurement.
Mm-hmm. Well, this could be done by systematic analysis of say, variance covariance matrix, and used to be such programs which allow to see which parameters are influenced mostly by given reflections, by given group of reflections, and the other way around, which reflections are associated with, have the biggest influence on particular type of parameters. So anyway, we have next question from or comment from Hans-Bert Birgi. The anomeric effects has nothing to do with hydrogen bonding. It's as LP to sigma sigma star effect.
Lone pair to sigma star is exactly the same mechanism as you would describe a hydrogen bond. So that is negative hyperconjugation. Of course, it's not, I'm not saying that the anomeric effect is the same as hydrogen bonding. I'm saying that the way of describing this kind of secondary overlap is the same. Mm-hmm. Lone pair or non-bonding orbital overlapping with an anti-bonding sigma orbital. Or I misunderstood. Maybe I can talk to Hans-Bert afterwards.
Yeah.
Dinesh Kulhari. Sir, can we find these interactions using SIF for the organic-inorganic hybrid perovskites single crystals such as NCH3, MnCl3? Maybe you can look into the chat to read the name of the formula.
I'm not sure if I understand the question.
I'm guessing if you can...
So a SIF file will only give you geometry and ADPs. Mm-hmm. So to do a bonding analysis, it's not in the SIF. So you can maybe use the SIF to start then with, if it includes the structure factors, with a Hirschfeld atom refinement or other ways. But the electrodensity information is not in the SIF. We know it at the moment. We are working on different SIF definitions, but is that the question?
It's most probably. Hans-Bert Birgi again. What is the evidence that the improvement in discrepancy factor R, for example, for alanine from 1.9 to 1.5% is statistically significant? Probably not the only parameter you have analyzed.
So what I can say is, I'm not 100% sure how to answer that question, but what I can say is that whenever we have, let's say, a drop of an R value that is in that small, then I would never use the R value alone as an indicator for saying that it's physically meaningful. So that is when we look into electrodensity distributions, into residual density maps, into bond topologies, into the results from the fitting, and compare those with reference techniques, for example, higher quality theoretical calculations, to let's say to ensure that the trends we see are physically meaningful. Certainly, there have been cases that we analyzed where the opposite was true, where the R value increased from Hirschfeld atom refinement to wave function fitting by, let's say, 0.1%. But the differences in the density distribution in regions of chemical interest were still meaningful. And then, of course, the other way is also true, that a bigger drop in an R value could be something that is physically not meaningful, like ADPs. No, I mean, in the fitting, you don't change ADPs. But looking just at the R value is not a criterion for stating that the effect is statistically or chemically or physically meaningful. And I think that's something that the entire community has to be aware of. It's not just R values we need to look at.
Yes, exactly. Especially distribution of residuals and improvement in distribution of residuals is really important. Joseph Kozishek is asking, is it true that the future of experimental electronic structure is in precise low order data? Higher order data suffers from a lot of noise. Can you comment on this?
That's basically the point I was making, that if we include high order data, we need to make sure that they are statistically significant and that they have been determined reliably. So what we do is, for example, for every normal measurement, we look at the statistics of the internal R value versus resolution, and then we cut. Our criterion here is I think 12%. So the resolution shell, that all the resolution shells that exceed internal R value of 12% or 15% will be cut away, because that way we add more and more noise into the data, which is so people measure empty space on the detector and claim that has been the resolution. No, I think we need to look at where are the data still significant above the noise level.
Thank you.
And a comment from Florian, please. It is hard to define the leverage for wave function fitting, because we have this problem of probably, right, that we are not directly refining parameters, right?
That's of course also a point. I mean, independent atom model and Hirschfeld atom refinement are least squares procedures. When we go to wave function fitting, that's not a least squares procedure anymore. So we are actually, when we compare those statistics, we have to be careful that we not overinterpret that, because we come from a background of least squares, but in fact, the fitting is something else, right? We have tens of thousands of molecular orbital parameters that we fit to maybe only a few thousand reflections. So this is not a least squares refinement.
Stefano Rasioppi, I'm sorry, I'm not pronouncing it well. Hi, thank you very much for a nice talk. I have 3 questions, 2 shorts though. The first one, I did not understand which EDA method you used. Was it the Morokuma or the Ziegler?
Yeah, okay. It was not the Morokuma, it was the Ziegler, but I didn't want to go into detail there, because we did something in the supporting information of that paper, something crude, where we used many different model calculations and subtracted them from each other. So I was happy to just say EDA. It's not the old classical Morokuma way.
The second question, when you showed the resonance percentage comparison, B3LEAP looked very similar to Hartree-Fock. have you tried pure DFT functionals instead, either GGA or meta GGA, but not hybrid?
Yeah, that's a good question. No, we have not. But I think since these, for example, this NRT method is, how should I say, you don't see gradual differences. You always have more like a catastrophe. Either it's that result or the opposite. That would be a good proxy actually for looking at different functionals. That's a good idea.
And the third question, I missed the connection between using conjugated methods to study chemical bond and the gaining of chemical information. Gernot Franking was used to use EDA plus QTM to get different insights from the two methods. However, in your example, I had a feeling that only EDA and BO could give a quantitative interpretation, and that the use of multi-methods was just to check what was the statistically more frequent interpretation, instead of gaining new insights for different methods. I have probably missed this important connection, but I would like to hear your comment. So it's rather a question about the different complementary view or methods which are giving you the same answer.
I think this is hard to respond to, because if you claim that only what I have on the screen now, I'm not sure if you see that anymore, the EDA and the NRT or NBO type, if you say that only that gives quantitatively correct information, then how do you say those? I mean, how do you know? So why is that the quantitatively correct information? Why is not the basin, the count of the electrons in these basins or the atomic charges the quantitatively correct result? I don't see how we could say that a certain combination gives the truth. I mean, we never get the truth anyway, but shows us the truth, and a different combination does not. So I think the comment that looking at how many methods, so what gives statistically to all these methods more answer A and more answer B, that's actually a good way. I think that's exactly what we should do. Look at all these different methods and then have a look which one is maybe an outlier and which give us a similar interpretation. But since all of these bonding descriptors always depend on a certain theory, on a certain approximation, on a certain philosophy, I think there is no way of saying that, for example, EDA plus QTAM is the correct way. I think that would be, we simply don't know that.
Stefano Rassoppi, that sounds great. Thank you so much for your comments, Simon. So it's just an acknowledgement of your answer. I do not see more questions nor comments. Thank you very much for the discussion and for your great talk.